Hey there, we're going to go over some kinematics equations. And so the word kinematics actually just means motion math. And as you can see from this definition here, there's a lot of math that we're going to be doing. And rather than me just giving you these four kinematics equations and saying, all right, go and use them, we're going to take the time and kind of see where they come from, derive a couple. That way, hopefully, you can see that you've actually been using these equations, a lot of these equations so far this year, and hopefully make it a little easier once it's time to start actually applying these equations. And the first two kinematic equations, they come from work that you've already been doing this year with a velocity time graph. So velocity versus time graph, we've done two things with these. Okay, the first one is we found the slope. And remember, the slope is equal to the acceleration. Okay, this is something we've been doing since the beginning of the year, and that's where we got this first equation for acceleration that we used, and that was acceleration was equal to your change in velocity, or your change in y, over your change in time, which was your change in x. Now on the equation chart, they just have it written where it's solved for the final velocity, so let's go ahead and do that. So the change in velocity is just final minus initial. And if we're trying to manipulate this equation for the final velocity, first thing we would do is multiply both sides by delta t. So that's going to cancel out, and you're going to be left with acceleration times time is equal to the final velocity minus your initial velocity. And then lastly, we would add initial velocity to both sides. And what you're left with is the final velocity is equal to the initial velocity plus acceleration times time. And this is your first kinematic equation, okay, as written on your equation chart. So it's one that you've been using all year, and that's our first kinematics equation. The next one also comes from work that you've done this year with a velocity time graph. This time, let's go ahead and draw our graph out. So here's velocity versus time. Let's make a line here. Now let's go ahead and label a couple points on here. Let's say this right here, that would be my initial velocity. And right up here would be my final velocity. And let's say this is your time t. And one thing that we've done with a velocity time graph, we found the slope, but we also found the area underneath the curve. And if you remember, the area under the curve was equal to your displacement, your delta x. So this is how we're going to actually derive our second kinematic equation. So if we broke this up into two shapes, we would have this rectangle here on the bottom, and then we'd have this triangle here on the top. And the area of the rectangle plus the area of your triangle is equal to your displacement. Okay, we've done this year. So let's build our equation from this. So for your rectangle, the area is equal to length times width. Okay, and the length here is going to be your t, I'm sorry, your v naught, and then your length there is going to be t, or delta t. And so the area there is v naught t. Now for your triangle, remember triangle is 1/2 base times height. So it'd be 1/2. Your base here is going to be t. And then your height, now this is from here to here is v naught. From here to here is v. So that means this little section right here is going to be v minus v naught. So v minus v naught. So the total area of this is going to equal V naught T plus 1/2 V minus V naught times T. And that's going to equal the displacement, or delta X. So we're going to do a little bit more deriving here, so we can combine some of these like terms because we have that V naught in there twice. So first step is let's distribute that 1/2 and that T into this parentheses right here. So I would be left with V naught T plus 1/2 V times T minus 1/2 V naught T. And again, that's equal to delta X. And if I look at this, I can combine this V naught T with this V naught T. Okay, so it's like 1 V naught T minus 1/2 V naught T. And then what you're left with is just 1/2 V naught T. So let's go ahead and rewrite that. Okay, and if I look at this, both of these terms here have a 1/2 in it, and they both have a T in it. So we can go ahead and pull that out, and I would be left with 1/2 V plus V naught times T, and that's equal to delta X. I need to rewrite that one a little bit better. And this right here is going to be your second kinematic equation. Now this one right here is not going to be, you're not going to find this one on your equation chart. But knowing where it came from, and it's just the area underneath a velocity time graph, is helpful because if you ever have to use this equation, you could apply it and derive it from a velocity time graph. So the third kinematic equation is just going to put both of these first two together. Okay, so we're going to combine this first one that we learned right here with the second one that we learned right here. And that's going to give us our third kinematic equation. So let's go ahead and rewrite this one over here. We had 1/2 V plus V naught times T equals delta X. And up here, your first one we found final velocity equals initial velocity plus acceleration times time. Now there's a lot of times where we don't really know the final velocity. So we're going to do a substitution here. Okay, for this final velocity, we're going to plug in this right here, and then we're going to do a little bit of deriving. So if I do that, I have 1/2 parentheses V naught plus acceleration times time plus V naught times T, and again that's equal to delta X. So what we can do is we can add this V naught with this one, 1/2 2 V naught plus AT times T equals delta X. Now we're going to go ahead and FOIL in that 1/2 and that T. So that would give me 1/2 times T times 2 V naught plus 1/2 times T times AT. So we just FOILed that in. And it equals your delta X. So over here, this first term, the 1/2 and the 2, that's just going to cancel out. And I'm left with V naught T plus, now this T times T, I'm going to be left with T squared, 1/2 A T squared equals delta X. So this is our third kinematic equation. And this one is written on your equation chart, so you don't have to memorize it. But I wanted to show you at least where it came from. So there's three of the four equations that we're going to be using. And for your last one, it comes from, again, something you've already been doing this year, and that was with our work and energy unit. So thinking back of that last unit, we know that work is equal to change in energy. And we know work is equal to that parallel force times distance. And so we're going to derive our last kinematic equation from this here. Now, let's say that that change in energy is kinetic. So it would be equal to change in kinetic energy. Change in kinetic energy would be your final kinetic energy minus your initial. And again, we're setting that equal to work. We also know work is equal to that parallel force times distance. So for kinetic energy, it's 1/2 mv squared. Your initial would be 1/2 mv naught squared equal to force times distance. Now for your force here, remember back in Newton's second law, we said acceleration was equal to net force over mass. If we rearrange that for net force equals mass times acceleration. We're going to plug that in for this force. This g here, we're just going to change that to a delta x. So now I'm left with 1/2 mv squared minus 1/2 mv naught squared equals, let's go ahead and do our substitutions, mass times acceleration times delta x. Now looking at that, they all have a mass. That cancels. So I'm left with 1/2 v squared minus 1/2 v naught squared equals a delta x. Okay, so from here, we're going to rearrange this for the final velocity. So I'm going to add 1/2 v naught squared to both sides. So I got 1/2 v squared equals 1/2 v naught squared plus a delta x. Now I'm going to multiply both sides by 2 to cancel that out. So all this is going to get multiplied by 2. And I'm left with the final velocity squared is equal to, now FOIL that 2 in, 2 times 1/2, that just leaves me v naught squared plus 2a delta x. So there's my fourth kinematic equations. So all these four equations that we just looked at, you actually have some experience using these equations that we've done throughout the year. So let's go ahead and kind of rewrite them all again. We have v is equal to v naught plus acceleration times time. We have x, or delta x, is equal to 1/2 v plus v naught times t. Delta x is equal to v naught t plus 1/2 at squared. And then lastly, we have v squared equals v naught squared plus 2a delta x. Now, one thing to note here if you look at the equation chart, they actually break this delta x into your final minus your initial. Okay, so if you see that, don't get confused, it's the same thing. So on the equation chart, it says x equals x naught plus 1/2 v plus v naught times t. Or for this one, on your equation chart, it'll say x equals x naught plus v naught t plus 1/2 a t squared. They're the same equation. The equation chart just breaks it up into your final and your initial displacement there. Now, it might seem like that's a lot of equations to work with. It's going to be really difficult. But when you're solving these problems and you're using these problems, think back of the problem solving strategy that we talked about in class, and that was our guess method. Okay, always write down what's given, the unknown, then you can pick your equation based off of that, substitute and solve. So let's do a couple practice problems together using these new kinematic equations. So this first one says a car slows down and it's going from 30 meters per second to 10 meters per second, and it does it in 5 seconds. We want to know how far it travels. Okay, so how far it travels, we're solving for that delta x there. So let's write down what's given. What was given here was, since it's slowing down from, that's my initial velocity. So your initial velocity is equal to 30 meters per second. 2, so that's going to be my final velocity. And 5 seconds, that's going to be your time. So there's my given information. I'm solving for that delta x there. So to pick out these equations, kind of the general rule of thumb here is to figure out which variable the problem is not giving you and you're not solving for. There's always going to be one variable that you don't care about. And looking at all the different variables, okay, you have initial velocity, final velocity, time, you have displacement, and then you also have acceleration. One of those, the problem isn't going to care about. Okay, we're not solving for it. It's not given. That's how you pick the correct kinematic equation. So looking at this one, nowhere on here in my given or my unknown information is acceleration. So I need to find a kinematics equation that doesn't involve acceleration. And there's only going to be one. So going back, looking through here, the one that doesn't involve acceleration would be that second one, delta x equals 1/2 v plus v naught, then times t. So that's the equation I'm going to use. So it's actually pretty easy figuring out which equation to use. You just identify which variable the problem doesn't need. So let's rewrite our equation. Delta x is equal to 1/2 v plus v naught times t. Now we can just plug and chug. Okay, we can start solving. So delta x is equal to 1/2. Final velocity is 10. Initial velocity is 30. And then your time is 5 seconds. So remember, do the inside parentheses first. So 40, half of that times 5. Now, sometimes the kinematic equation you need to use isn't set up to where your unknown is what the equation is. So sometimes you do have to manipulate your kinematic equation a little bit. This time it worked out nicely where we didn't have to do that. Let's work one more together. So this one says a golf ball has a velocity of 6 meters per second when it begins to roll up a ramp. That's going to be my initial velocity. And it rolls up a ramp after traveling 4 meters, so we have that delta x. It has a velocity of 4 meters per second, so that's going to be my final. And they want to know the acceleration. So we wrote down what's given and what's unknown. Now we need to identify which variable we don't care about in this problem. Okay, and if we're looking at it, we don't need time. So we need an equation that doesn't involve time. Now, one question you might be asking yourself is, what about you have this delta x, but on the equation chart, it's written as your final and your initial. A lot of times you can make the assumption that your initial displacement is at 0 meters, which is why we can leave it in that delta x. Unless a problem tells you you're starting at this displacement, you're ending at this one, that's whenever you would be, you'd have to kind of look out for that. So we need an equation that doesn't involve time. And again, there's only going to be one. And looking at your equations, it's going to be this one right here. So let's go ahead and rewrite that equation. We have v squared is equal to v naught squared plus 2a delta x. Now this is one of those problems where it's the equation we need to use, but it's not set up to solve for acceleration. So we got to move some things around. So we're going to subtract v naught squared to both sides. So I have v squared minus v naught squared is equal to 2a delta x. We're solving for acceleration, so I'm going to divide by 2 delta x. So that cancels this and that. Acceleration equals v squared minus v naught squared all over 2 delta x. Now we can plug in our numbers. And after you plug this in, you end up with negative 2.5 meters per second. And it's negative because it was slowing down.